Hi, you guys. I'm going to work through the key for this bonding POGIL and also the hydrosphere bonding review, since we don't have the advantage of talking to each other about it in person. So to start off, if we look at the key for Model 1, so here's the key. What do the two shaded regions represent? So the light shaded region is the outer electrons, and then this inner shaded region, that's the inner electrons. And the only electrons that really do chemistry are these outside valence electrons, and so we're going to be pretty focused on those. This asks us where are the protons located in this model of the atom? Can you see them? What charge do they have? So they are in the nucleus in the middle. We cannot see them because they're too small, and they have a positive charge. Number 3, we can go ahead and skip because it is beyond the scope of this class. So for number 4, describe 2 or 3 differences between separated atoms and bonded atoms. So separated atoms each have their own outer cloud and inner cloud. Bonded atoms could have one that only has inner electrons and one that only has outer electrons. It could share electrons and be kind of connected by electron cloud in the middle. And then it could have an electron cloud that sticks out one side, or it could have an electron cloud that is symmetrical on both sides. And that's all very different from our non-bonded atoms. So if we're looking at our ionic bonded atoms, what happened to the electron distribution when the ionic bond was formed? So the outer electrons were transferred to another atom, but the inner electrons and nucleus are unaffected. Oops. Okay. So here's our visualization for ionic bond. Draw the charges that would be formed. So since this one lost, the one on the right lost its outer electrons, it's going to become positive because it lost electrons. This one that's over here on the left, it gained extra from the outer shell, and so it has extra valence electrons now, so it has a negative charge. If I look at the representation of the covalently bonded atoms, the electron distribution kind of changed because the outer electrons moved to fill the space between the two atoms. But the inner electrons and nucleus are unaffected. So that's kind of similar to ionic bonds. The inner electrons and nucleus are unaffected. Number 8, how are ionic bonds and covalent bonds different in terms of electron distribution? So in the covalent bond, most of the electrons are distributed between the two atoms, and in the ionic bond, most of the electrons are distributed on only one of the two atoms. So that's kind of the difference between those two. Looking at the visualization of the polar covalent bonded atoms, what happened to the electron density when the polar covalent bond was formed? So, the outer electrons moved more to the left side, but inner electrons and nucleus were unchanged. Okay, so how are polar covalent bonds how are polar covalent bonds different than regular covalent bonds in terms of their electron densities? How are they similar? So they're different because one atom has more electron density, so that in this case that would be the left one right here, and one atom has more electron density, but what's similar is both have electron density between the atoms. All right. How are polar covalent different and similar to ionic bonds? So they're different because in ionic bonds, electron density moves entirely to the other. That's an R, it looks like a B. Entirely to other atom. But they're similar because they're not sharing electrons equally. Okay. What happens in terms of charge when you have a greater density of electrons on one side of an atom than on the other side? So if you have a little bit more electrons, you're going to be a little bit more negative. Okay, so that means one side of the atom is going to be a little bit more negative than the other. So now it gives us a nice definition. In chemistry, there is only a slight charge created by a shift in electron densities. We like to say there's a partial charge, or so we call these charges dipoles, and we represent dipoles with the lowercase Greek letter delta. So positive is delta plus, negative is delta minus. So then it says, go ahead and label this atom. So this is going to be delta positive, and this guy's delta negative. My deltas are horrible. Please don't judge me. They look like music notes, kind of. Okay, so the next question we need to consider is how on earth do we wind up, with most of the electrons over here and not as many over here on the right? And that comes down to something that we call electronegativity. Electronegativity, and we're going to talk in a lot of detail about electronegativity this week. It's just an introduction. But electronegativity is the ability of an element to draw electrons towards itself when it's bonded to something else. So these values are based on measurements that we make. And there's many different scales used by different chemists, but this is the one that we are going to use to calculate electronegativities. So there's numbers on this little periodic table, and those numbers are the electronegativity value. So the noble gases do not have an electronegativity value because they don't need any more electrons. They already have 8. So they also don't form bonds. So their octet rule is already satisfied. One element is out of its normal position. So that's hydrogen. And the reason it's been moved is really just because its electronegativity is much higher than the family where it usually resides. So it is double that of lithium, and it really fits in better around boron and carbon, which are closer to its numerical value. So that's why hydrogen is moved. So we can use this table to determine some electronegativity values. So if we look at hydrogen, it's just 2.1. Oxygen's is 3.5. So I'm just literally looking at this number. Potassium, 0.9. And chlorine is 3.0. So it says what has the highest electronegativity values. So I'm going to go ahead and erase these circles so that I can circle the ones with the highest. And we can see definitely fluorine is the highest at 4, followed by oxygen at 3.5. And then chlorine and nitrogen are kind of tied at 3.0. So I'm actually ended up drawing 4 circles. And now I'm going to erase them because I can't see because of those circles. Okay. Then it says what's the lowest. So the elements that have the lowest are right here: francium, rubidium, and potassium. They would rather give away an electron to get to 8 than gain an electron. So they are not good at attracting electrons. So francium, cesium, rubidium, and potassium have the lowest electronegativity values. Really for 19, we probably don't need to answer that either. It's going to be on the scope of our class. Sorry about that, you guys. I thought that I had already revised this for you, and apparently I didn't use the revised version, so now I feel kind of silly, but whatever, we'll survive. One way we can characterize a bond is by saying if it's more ionic or covalent, and if it's polar or not. So covalent bonds, they're sharing equally, so they should have a small difference in electronegativity since they're sharing equally. An ionic bond should have a large difference because they're not sharing equally. So in the game of tug of war in covalent bonds, nobody is a clear winner. They're kind of pulling equally. But in an ionic bond, somebody is so much stronger, so much more electronegative that they can just steal the electron all the way away. Okay, so it asks us to calculate our differences in electronegativity. And so you can just take the values from the table and work those out. So carbon minus hydrogen, that value is 0.4. Now that I have all my values from subtracting the value of one element to the value of the other element in the compound, we can predict if they are ionic or covalent based on the difference. So if it's a little difference, they're going to be covalent. Oops, covalent. Big difference, 3, that's going to be ionic. Something in the middle will probably be polar. So like CLF, I would expect to be polar. This one is probably just covalent. This one